So the title of this one is Paging Doctor Attention, and trust me, it's for a really good reason. We're about to dive deep and diagnose one of the biggest, but maybe most invisible problems in the world of AI, its massive memory crisis. You know the drill, right? You ask an AI a question, and boom, seconds later, you get a reply. It feels like magic. We always think about the raw intelligence of the model or the speed of the computer chips, but what if I told you the real magic isn't just about pure power? That's right. The secret to how these systems can serve millions of us all at once isn't just about having faster processors. It's about being incredibly clever and solving a really tricky puzzle with a limited resource, memory. So let's unpack how they pulled it off. But to really get the solution, you've got to understand the problem first. It turns out every single conversation we have with an AI has a hidden cost, and it all boils down to that memory puzzle. Okay, the best way to wrap your head around this is to think about packing a suitcase. If you just kind of throw your stuff in there, you get all these weird gaps and empty spaces, right? A ton of wasted room. Well, the exact same thing happens inside a GPU's memory. It's called fragmentation, and it's a huge problem. You end up with all this wasted space. Some of it's reserved but unused, some is inside the chunks of data, and some is between them. And here's the kicker. That messy packing job is what directly limits how many people can use an AI service at the same time. So what's making this such a mess? Well, let's meet our culprit. It has a super technical name, but its job is actually pretty simple. It's called the KV cache. Now, before we get to the KV cache, we got to talk about the big idea behind modern AI, the attention mechanism. And don't worry, we're skipping the heavy math here, because the core idea is actually super intuitive. Attention is just how the model figures out which words in your question are the most important, so it can give you a good answer. It's how it knows what to focus on. And this is where it gets really cool. To come up with the very next word, the model sends out what's called a query. It's basically asking itself, okay, based on everything so far, what's the most relevant thing to say next? It then compares that question to the keys from all the previous words to figure out what's important. It's like a tiny little relevance search happening for every single word it writes. Now, you can imagine doing that calculation over and over and over again for a long conversation. No way. That would be painfully slow. So the model has a cheat sheet, the KV cache. This is where it stores all those key and value results from the words it's already processed. It's basically the AI's short-term memory for your conversation. And this is the heart of the problem. That KV cache isn't some fixed size. It gets bigger with every single word the AI generates. And since my conversation with the AI is a different length than yours, the amount of memory it needs is totally unpredictable. This is what creates that messy suitcase problem we were talking about, all that fragmentation and wasted space. So, this memory crisis, it was a massive bottleneck, a real showstopper. You couldn't just keep throwing more expensive GPUs at it. You needed a smarter, more elegant solution. And that's when we got the first big breakthrough, a technique called paged attention. And this is just a classic example of where great ideas come from, right? The researchers didn't have to invent a whole new concept from scratch. They looked back decades to a tried and true idea from computer operating systems called paging, and they brilliantly adapted it for the world of AI. The difference here is so intuitive. Think about it like this. The old way was like trying to find one gigantic parking spot for a massive 18-wheeler right in the middle of downtown. Good luck with that. Page attention, on the other hand, breaks that big, clunky KV cache into lots of small, standard-sized blocks. So instead of an 18-wheeler, you've got a whole fleet of motorcycles, and you can just zip them in to any little open parking spot you can find. It's flexible and way, way more efficient. So how does it actually work? Well, it's a pretty simple three-step dance. First, it just chops up that growing, unpredictable KV cache into these neat, uniform little blocks. Second, because those blocks are small, they can be slotted into any free space in the GPU's memory, which pretty much gets rid of all that fragmentation waste. And third, it uses a simple map called a block table to keep track of where all the different pieces of the conversation are stored. It's simple, it's elegant, and it was totally revolutionary. Page attention was an absolute game changer, especially when it was implemented in a popular system called VLLM. But of course, in the world of AI, the story never ends there. The next step was to take this brilliant idea and make it even smarter. The thinking behind this next step, the attention, is actually really clever. You see, paged attention was like building a custom traffic management system just for our fleet of motorcycles. It worked great, but it was a lot of extra engineering. The attention had a different idea.
It realized that modern GPUs already have a super sophisticated traffic management system built right into the hardware. It's called virtual memory, so why not just use that?
And this visual really just says it all, doesn't it? On the left, you've got paged attention, which has to build its own map, the block tables, in software. And on the right, you have V attention, which just hooks into the map that the GPU hardware already provides, the page tables. It's the classic work smarter, not harder approach. It offloads all that heavy lifting from the software to the hardware, which is almost always a huge win.
And the payoff here, it's huge, especially for the folks actually building this stuff. It means way less custom code to write and maintain. Before, if you wanted to add a new optimized piece of code, you might have to rewrite hundreds of lines to make it work. With Vi Attention, it can be just a handful of changes. This makes the whole system easier to move to different computers and lets developers focus on the AI model itself, not on reinventing the wheel for memory management.
Okay, so we've been geeking out on some pretty technical stuff, but what does this actually mean for you and me? What's the real-world payoff of solving this memory puzzle? It all comes down to this number: a 2 to 4 times improvement in how efficiently these incredibly expensive GPUs can use their memory. That's a massive leap. And what that number really means is you can serve 2 to 4 times more people, handle 2 to 4 times more requests on the exact same hardware. This is the kind of innovation that makes these huge AI services actually affordable to run. It's what makes AI faster, cheaper, and in the end, more powerful and accessible for every single one of us. All right, so let's just do a quick side-by-side. Paged attention was the big breakthrough, right? It built a custom paging system completely in software. V-attention was the elegant next step, taking that same job and offloading it to the GPU's own hardware. They both tackle the exact same problem, but V-attention really points toward a future where we're working with the hardware, not just building on top of it. So we've just seen how one brilliant idea completely unlocked the scale of AI as we know it today. But this field moves at an unbelievable pace. As these models get more complex and start to reason in more sophisticated ways, it really makes you wonder, what's the next great bottleneck hiding just out of sight? And what brilliant idea is going to be needed to solve it?